This video is from the Foundation series of GMATMathPro.com and explores the basics of prime numbers. Specifically, we will look at three questions. 1. What is a prime number? 2. What is prime factorization and why is it useful? And 3. Why is 1 not considered to be prime? So the first question, what is a prime number? A prime number is an integer greater than 1 whose only positive divisors are itself and 1. And here, positive divisors just means factors. So another way to think of it is that a prime number is an integer greater than 1 with no factors other than 1 and the number itself. And here is a list of the first several prime numbers with the ellipses at the end indicating that the number of primes is infinite. And for the purposes of taking the GMAT, it's important to familiarize yourself with these first few prime numbers and be able to recognize instantly that they are prime. Now, if an integer greater than 1 is not prime, we call those composite numbers. And here is a list of the first few composite numbers, 4, 6, 8, and 9. So you can see that just kind of fills in the gaps that the prime numbers leave. So every integer greater than 1 is either going to be prime or composite. The final thing to highlight is if you look up here at the examples of primes, 2, 3, 5, 7, and so on, you'll notice that 2 is the only even number listed. And in fact, 2 is the only even prime number because every even number by definition is divisible by 2, and so being divisible by 2 automatically disqualifies all the other even numbers from being prime. The second question is, what is prime factorization? Prime factorization is the process of breaking down an integer into a product of primes. So for example, 21 is equal to 3 times 7, so it's a product of those two primes, 3 and 7. 24 is equal to 2 times 2 times 2 times 3, or the preferred way to write it would be just 2 cubed times 3. And so the next question would be, how do you find the prime factorization of an integer? And to explore that, we'll look at an example. So let's look at the number 84. If you want to find the prime factorization of a number, one thing you can do is use what's called a factor tree. And the way that works is you think of, in this case, any two numbers that multiply to 84. And so let's say you think of 12 and 7. So you just kind of write them on two branches of the tree, like that. Now you're going to go down each branch and keep factoring down that branch until all you're left with is prime numbers. Now 7 is already prime, so there's nothing more we can do there. 12 is not prime though, so we can keep factoring that, let's say as 4 times 3. And 4 is not prime yet, so we can factor that as 2 times 2, and now we're left with 2, 2, 3, and 7. So the prime factorization is just all those primes that you end up with multiplied together. And the preferred way to write that would just be 2 squared times 3 times 7. Now just to show you that it doesn't matter what two numbers we start with, we could have also started this off by saying 84 is the same as 42 times 2. 2 is prime, 42 is not, so we keep factoring 42. We can factor that as 7 times 6. And 6 we can factor as 2 times 3. And you see we end up with the same primes, two 2's, a 3, and a 7, so we have the same prime factorization of 2 squared times 3 times 7. So then the only question is, who cares? Why would you want to find the prime factorization of a number? And the answer to that is to some extent beyond the scope of this video, but the general answer is that when we look at a number's prime factorization, we can see properties of it that may not be obvious if we just look at the original whole number. So in this case, we can see instantly by looking at the prime factorization of 84 that it has two factors of 2, a factor of 3, and a factor of 7. And that kind of information is going to be incredibly useful when we do more advanced things like finding the least common multiple of two numbers or the greatest common factor. We can also use the prime factorization to determine if something is a perfect square or a perfect cube, and so on. But essentially, it's kind of like looking under the hood of a car. We kind of get a sense of what this number is made up of and what makes it work. And finally, why is 1 not considered to be a prime number? If you think back to the definition of a prime number, it specifically says that prime numbers are integers greater than 1. But why exclude 1 in the first place? After all, it seems like it fits the criteria, otherwise its only divisors are itself in 1. So it seems somewhat arbitrary to exclude 1 from the set of prime numbers. So why not just let 1 be prime? And there is actually a good reason for it, and it stems from something called the fundamental theorem of arithmetic, which you can see here says that any integer greater than 1 can be written as a unique product of prime numbers. So taking 21 again as an example, 21 can be written as 3 times 7. It's the product of those two primes, 3 and 7, and that's the only way to write 21 as a product of primes, so it's unique. But now if we decide just to let 1 be prime, suddenly this theorem doesn't work so well anymore, because now we could write 21 as 1 times 3 times 7, or 1 squared times 3 times 7, or 1 cubed times 3 times 7. We could go on and on forever, but all of these new prime factorizations of 21 are pretty trivial, because all we're doing is multiplying by different versions of 1. So the choice would be to either rewrite the fundamental theorem of arithmetic to explain these trivial exceptions, or just not let 1 be prime in the first place. And that's the simpler option. It keeps the theorem more elegant and simple. So that's why 1 is not considered to be a prime number.